Okay, well, let's take a look at an example problem from the chapter. Given a triangle with area K and semiperimeter S and in radius R, prove that R times S equals K. So, let's just sort of stand back and think about what that means. Is that the area of a triangle is equal to the semiperimeter of triangle ABC at times the in radius. It certainly seems like a crazy result that this would actually be true, but let's see if we can figure this out. So here we go. Let's kind of think about what we have. So we have a triangle. Let's go. Try to sketch this well. A, B, C. So that means that this distance here we'll call B. This distance here we'll call C. And this distance here we'll call little a. We think that there's an in circle inside here. See if I can get it just about right. There we go. Looks pretty good. So A, B, and C. We know that this thing has a center at I. And that these three distances, of course, will be the same. I don't know. Let's call this one U, V, and W. And now the proof, what it relies on, is in adding a few lines, and it turns out this is the right line to add here. And this one too. Okay, so here's our proof sketch. First, take a look at this triangle right there. In that particular triangle, the area, let's call it BIC, is going to be equal to 1/2 of BC times IU, which will be the same thing as 1/2 of A times the in radius, right? The in radius is just R. So the area of that blue triangle is given by that. We can play this game in three different ways, right? CIA, just got lucky there, I guess, is then going to be 1/2 the length of that side, which is BR. And let's see, AIB is going to be equal to 1/2 the length of the third side, which is C times radius. And we know that the triangle total would be the sum of those. Well, let me just make sure and draw them in. Maybe I draw them in here. I'll make this one pink. Make this one yellow. Let's see, so what we can prove then is that K of ABC is going to be the sum of the blue, the pink, and the yellow, right? So it'll be 1/2 AR plus 1/2 BR plus 1/2 CR. And I think it's pretty easy to see that this is the same thing as 1/2 R times A plus B plus C, right? Again, I didn't really draw it in, but of course these are our R's. It's the same thing as R times A plus B plus C over 2. And I think you can recognize that as RS. So indeed, the area of the triangle is given by the in radius times the semi-perimeter. I'm going to add one more page. It says to go ahead and use the result. So let's try this in blue. It says use the result. Use the result to express R in terms of the lengths of the three sides of the triangle. In other words, can we get just a formula that would give us the radius, the in radius, as a function of the three sides? It sure seems like that should be possible now that we have this. So the second half would be to solve this for R. So R is going to be K ABC over S, semi-perimeter, which we could say is the same thing as KABC over, well, this would be A plus B plus C over 2. Same thing as 2 KABC all over A plus B plus C. I see. I think the way that I did it in my notes, I'm looking at my notes again, might be a little bit different than what we're getting here. I think the easier way to do this would be to just leave it in terms of S. So I'm going to erase this. The reason I'm going to do that is because in this very next step, I can replace the area of the triangle as a function of its side with Heron's formula, right? We already have a formula that gives the area of the triangle as a function of the lengths of its side, and that's the one that we just got from Heron. So S minus A, S minus B, S minus C. This is by Heron's formula. But of course, that whole thing has to be over S. And when we bring the S inside of the square root, we've got to square it. And one term will cancel with, one of those squares will cancel with one of the S's on top. So on top we'll be left with S minus A, S minus B, S minus C. On bottom we'll be left with S. And indeed, here's the formula that's strictly in terms of the length of the side. Remember that the semi-perimeter is just A plus B plus C over 2. So this particular formula will tell us the in radius strictly as a function of the lengths of the sides. So if we have sides of length A, B, and C, we can find the semi-perimeter, find the product of semi-perimeter minus A minus B minus C, divide by the semi-perimeter square root, and that gives us our in radius. So pretty fantastic. It seems like that we can get all of that fairly easily. All right, that's the first example problem. Hope you liked it. I'll do one more in the next video.